we're going to prove one of the most important results concerning linear maps, which is the rank-nullity theorem. So to state the rank-nullity theorem, we need to know what rank and nullity mean. So if you have a linear map T from V to W, then the nullity of T is the dimension of its kernel, and the rank of T is the dimension of its image. So let's take a simple look at an example of rank and nullity for a linear map. I'm going to define T from R cubed to R squared by T of a vector x, y, z is going to be equal to x, y. Okay, this is a linear map. You should check the definitions that this genuinely is linear. And we're going to work out its rank and its nullity. So I think it's pretty clear that actually this map T is onto. Because if you give me any element of R squared, well, AB for example, then that's equal to T of AB0. Or AB1 or AB 1000, whatever. It's in the image of T. So the rank of T, being the dimension of the image, is the dimension of R squared, which is 2. On the other hand, if we look for the nullity, then we need to know about the kernel of T. So let's pick another color to work out the kernel. So T of x, y, z is equal to the 0 vector if and only if, well, what has to happen? Let's write this correctly. T is going to R squared, so the 0 vector in R squared is 0, 0. Well, when does this happen? We have to have x and y equal to 0. So x equals y equals 0. Okay, so the kernel of T is all the vectors of the form 0, 0, something. 0, 0, z for z in the real numbers. So that's a one-dimensional vector space. It has as a basis the single vector 0, 0, 1. So if you look at the kernel of T there, it's clear that that general element that we wrote down just here is actually just the same thing as z times 0, 0, 1. So every element in the kernel is a scalar multiple of 0, 0, 1, and therefore the kernel is one-dimensional vector space with 0, 0, 1 as one of its bases. In particular, it's got a basis of size 1, so it's one-dimensional. Okay, so we know the rank and the nullity of this linear map. And one thing you might notice here is that if you add the rank and the nullity, you get 2 plus 1, which is the same as the dimension of the vector space, which was T's domain. So 2 plus 1 is 3, and the dimension of R cubed is 3. That's not a coincidence. It happens everywhere, it happens always, and its name is the rank-nullity theorem. So let's now state and prove the rank-nullity theorem. You take a linear map T from V to W, and then what it says is that the rank of T plus the nullity of T is equal to the dimension of the domain of T. So let's just remind ourselves of the definitions. The rank is the dimension of the image of T, and the nullity is the dimension of the kernel of T. And that is equal to the dimension of V, the domain of our linear map T. So let's do a proof. We begin our proof by saying that we know that the kernel of T is a subspace of V. So we're going to take a basis for that subspace. We're going to let K1, K2, K3 up to Km be a basis of the kernel of T. And if you think of those elements K1 up to Km as just being things in V, they form a linearly independent sequence in V. They might not span all of V, in fact usually they won't, but they will be a linearly independent sequence in V. So every linearly independent sequence can be extended to a basis. So we can add some more vectors to get a basis of v. So we'll do that here. We'll let the extended, the basis of v that we get by adding in some vectors be k1 up to km, and then some other vectors v1 up to vn. Now what I claim is that a basis of the image of t is t of v1 up to t of vn. And I'm going to prove this in a moment, but let's think why it's enough to prove that. Because the reason that it's enough to prove that is that if so, then the dimension of the kernel of t, so the nullity of t would be m, because our basis for the kernel had size m, and then the rank of t will be equal to n, because there was a basis t of v1 up to t of vn, and the basis the dimension of v would be, well, we have a basis of v consisting of the k's and the v's, and in total there is n plus m of those. So if we proved that t of v1 up to t of vn was a basis of the image, then the rank nullity theorem would follow, because the dimension of v was n plus m, the nullity was m, and the rank was n. So that's all we need to prove. Let's try doing that. We have to do two things if we want to prove that's a basis. We have to prove that it is a spanning sequence and that it's linearly independent. So our first claim is we're going to try and prove that t of v1 up to t of vn are a spanning sequence for the image of t. So if we let t of v be an element of the image of t. So that's what elements of the image look like. They look like t applied to a vector v belonging to capital V. Now we have a basis for v. So that basis is k1 up to km followed by v1 up to vn. So I can write this vector v belonging to capital V as a linear combination of that basis. So there are scalars a1 up to am and b1 up to bn such that v is equal to the sum of the ai ki's plus the sum of the bi vi's. Okay, that's simply because the k's and the v's form basis for capital V. Okay, now t of v is, using the linearity of t, we can write it as the sum of the ai t of ki's plus the sum of bi t of vi's. So remember, t is a linear map, which means it respects addition and scalar multiplication. So if we use that property a lot of times, then the result is this. But of course, the k's are supposed to be in the kernel of t, so t of ki is always the zero vector. So that entire first sum is just lots of zero vectors. So we can ignore it. We just have the second part of the sum. Let's just annotate that to say why it was. Why is this? These are all the zero element in W, the zero vector in W, as ki is supposed to be an element of the kernel of T. Okay, so what have we got there? What we have is a linear combination of T of V1 up to T of Vn. So that is in the span of T of V1 up to T of Vn. Okay, we have proved that every element of the image is in the span of T of V1 up to T of Vn. So we've shown that that sequence, T of V1 up to T of Vn, is a spanning sequence for the image. Let's now show that they are linearly independent. So linear independence. So let's suppose that we have a linear dependence relation on the T of V1 up to T of Vn. So some linear combination equal to the zero vector. So we'll suppose that the sum of, let's say, Ci times T of Vi is equal to the zero vector. So that sum should go from 1 to n. Okay, again we're going to use linearity. This is the same as T of the sum of the Ci Vi's. Okay, so again, this is just because linear maps have to respect scalar multiplication and addition, so if you use that property lots of times, you can see that T of the sum of the Ci Vi's is the same as the sum of Ci times T of Vi. Okay, what does that tell you? That tells you that the sum of the Ci Vi's belongs to the kernel of T. It's in the kernel. We've got a basis for the kernel. So we can write this vector, or this element of V, as a linear combination of the basis elements for our kernel. So we could write it, let's say it's di, the sum of di ki. Where do these sums go? That one goes up to n, and this one will go to m. Okay, but if you move this around, so if you subtract to the right-hand side from the right-hand side, you get the sum of the Ci Vi's minus the sum of the Di Ki's was equal to the 0 vector. But the vectors k1 up to km and the vectors v1 up to vn form a basis for V. In particular, they're linearly independent. So this whole sequence is linearly independent because it was a basis for V, so all of those scalars must be 0. In particular, all of the C's have got to be 0. Right, we've shown that the T of Vi's are linearly independent because we began with a linear combination of them equaling the 0 vector in W, and we've proved that the coefficients in that linear combination actually all have to be 0. So that's our proof of the rank-nullity theorem. Let's take another example of applying the rank-nullity theorem. We're going to look at our differentiation map on the vector space of all polynomials of degree at most n in a single variable x. So our map is called D. It goes from the polynomials of degree at most n in one variable x to the same place, and d of a polynomial f is the derivative df by dx. So let's look at what's happening here. Let's think about what's going on. So one part of this, I mean, if we're interested in the rank-nullity theorem, we're interested in the kernel and the image. But the kernel here is the easy part. So the kernel of D is the set of all polynomials in the variable x of degree at most n whose derivative is 0. And you know that the only polynomials with derivative 0 are the constant polynomials. In fact, every constant polynomial has derivative 0, so this is all constant polynomials. But a constant polynomial is just a scalar multiple of the polynomial which is 1 everywhere. So it has the constant polynomial which is just 1 everywhere as a basis. Right? Every constant polynomial is a scalar multiple of the constant polynomial 1, so that means the constant polynomial 1 spans, and since it's just one vector on its own, one non-zero vector on its own, it's linearly independent. So it's a basis for this kernel. So we now know that the dimension of the kernel of D, which is the nullity of D, is 1. And now the rank-nullity theorem tells us something. So by rank-nullity, the dimension of the image of D, so the rank, plus the dimension of the kernel of D, which is 1, is equal to the dimension of the vector space, which is the domain of V. So this vector space, this domain, well, it's the same as the codomain, has basis 1x x squared up to x to the n. So there are n plus 1 things there. The dimension of the vector space of polynomials of degree at most n is n plus 1. Okay, so we now know the rank. It's n. And this is actually a helpful thing to know because you have seen some tricks for finding dimensions of vector spaces, and we saw some results on subspaces. So let's see why this is useful for pinning down exactly what the image is. So if a polynomial f has degree at most n, then its derivative, d of f, has degree less than or equal to n minus 1. Okay, what does that tell you about the image of d? So the image of d is contained in the polynomials of degree at most n minus 1 in x, because when you differentiate a polynomial of degree n, you get a polynomial of degree at most n minus 1. So the image is contained in there. In fact, even better, the image is a subspace of there, because the image is always a subspace. We proved this when we learned about kernels and images. Okay, so the image is a subspace of this, and it has the same dimension, because we saw the image of D had dimension n. That's the same as the rank. And we know that the dimension of the space of polynomials of degree at most n minus 1 is n. Right, if you have a subspace of a vector space and they have the same dimension, then the subspace is the whole vector space. We proved this when we were looking at dimensions of subspaces. So the image of D must actually be all of the set of polynomials of degree at most n minus 1 in X. So this is one reason why the rank-nullity theorem is useful. We can use it to help us in identifying certain subspaces, because the rank-nullity theorem actually tells us what their dimensions are.